All right. All right. So yeah, my standard error is 4. What does that mean? Oh, I love everything you're saying up top. Okay. No. So if we're, and all of that is correct, but that standard error value for someone help us out. Like what is the literal interpretation of that standard error? Exactly. Beautiful, right? The sampling distribution. I would expect on average, any randomly selected sample of 25 is going to bounce around about on average from the population mean of 80, right? Now that does that mean that I can't get sort of scores that said no, but on average, I'm sort of, this is sort of about how far would we jump around? Should I expect the means to jump around based on this? Now, is that a big value or a small value, Abby, in this context? I'd say it's pretty big, right? Like in terms of if I've got for my whole distribution, if the or excuse me, the standard deviation is 20, that's actually quite a lot of jumping around and stuff like that. And part of that is recognizing that we've got a sample of 25. That's small, right? We're going to get quite a lot of sort of variability there. But to Daniela's point, we'll go through and actually calculate here. So this is giving me characteristics of my mean, my sample mean, as opposed to sort of characteristics of an individual score. I go through and I take my observed mean, what I've got, what I expect under the null, right? So I've got a difference of 8 points divided by 12 divided by my standard error, and I get a z-score of 3. Okay. Then if I go through and calculate my confidence bound, this is just my observed mean plus or minus, because we're using z statistics, 1.96. That's just my level of precision for my 95% confidence interval. Multiply it by my standard error, and I get a lower bound of 84.2 and an upper bound of 99.8. Okay. So just based, and so I really don't care, like sort of the z-score is boring. If you know something about z-scores pretty big, right? And so we can kind of already start to assume. But looking at that confidence bound, what can I already, Lindsay, start to think about and sort of what inferences might I draw already just based on looking at that confidence bound? What's my presumed value for cognitive functioning under the null hypothesis? Okay, is 80 a reasonable value? Is that a data supported value? Right. So already I know that my value assumed under the null doesn't fall in my confidence bound. Like, could it be 80? Sure, but it's not something that's supported by my data, right? And so already, if I start falling back on, I'm just really invested in yes, no decisions about reject, fail to reject. I already know what I'm going to do, right? Do I need a test statistic? Do I need a p-value? No, my confidence bounds already tells me I'm just a real hard up to make a yes, no decision. The z-test isn't even needed because I can just look at my confidence bound and look, does my null value fall in there? If it doesn't, then I'm going to fail or then I'm going to reject. If it does, then I fail to reject. The only thing that we're going to get out of that z value is just the z-score is just a p-value, right? But looking at this, and this kind of is bouncing off sort of the thing that we were asking about, Abby, is what about anything else that you're sort of looking at that confidence bound? Any other inferences that you might start to draw from that? What else are you getting from that confidence interval? Helper, you got your hand up. Yeah, it's super wide. So we're saying, in this scenario, what's my best guess for average cognitive functioning in older adults taking supplements? Yeah, what is it? 92. Why is it 92? best guess, right? But my data will support anything from 84.2 to 99.8. That's pretty massive, right? And so, sure, my and sort of jumping ahead a little bit, what might I infer based on these data about sort of the impact of supplements? What's that? Well, I know the average score in the just older adults in general is 80. Is 80 a value in there? There is an effect, right? Okay, so I'm not going to say, but it does suggest that there may be effect. But Gabe, what does this tell me about sort of the magnitude of that effect? Yeah, it's super variable. I don't know. It's anywhere from my data would support it sort of an increase of anywhere from about 4 points to 20 points, and that's pretty wide, right? And so wanting to think about sort of just like there's sort of rich information, like it's a nerdy thing to say, but like these interval estimates just tell you so much information about what's going on. If you can push yourself off of just being jazzed about yes, no decisions on effect or not, right? In this data, it's sort of like we're saying that, yeah, in this scenario, we already know that I'm probably going to that I'm going to reject, not probably, I am going to reject the null hypotheses based on sort of the boundaries I've set. And so our data are consistent with the idea that supplements might be useful. If I'm an actual applied person, am I super excited about this? I don't know. A lot of imprecise, like, I don't know, right? If these are just something that I can take and it doesn't have any side effect and it's just like me taking some supplements, cool, whatever. But if you give me GI distress and stuff like that, I'm like, oh, I don't know. Like, to what extent, like, how much do I want to get invested in this? How much of an influence am I actually going to get, right? So thinking about all of this, okay? Okay, so scenario 2, changing things, sample size, but we got a score of an average of 84 points on my neurological assessment, okay? Same thing, I mean, same scenario, so just going through, everything's identical. Now I have a different point estimate, right? Gabe, now, what am I getting in terms of my confidence bound for scenario 2? Pretty large. It's going to be the same size as the one before because everything going into it is the same. 91 point, yeah, 8. Okay. Yeah, 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 yeah. So, my best guess is that the population value for older adults taking supplements is 84. It's not 80, right? But do my data support a population value of 80? Yeah, they do, right? And so already I know just based on sort of my interval estimate that I'm going to reject or that I'm going to fail to reject the null hypotheses. That my null value is compatible with the data that I've collected. It's not consistent with my best guess, but it's certainly reasonable based on sort of what I've gone through and collected. And these data now, my interval estimate is saying like that I've got anywhere from about a 4-point reduction in cognitive functioning to a 12-point increase, right? Interpretations and sort of giving you words to substitute instead of significant, not significant, right? Things like, so these are compatible, sort of the data, sort of the null hypothesis or the null value is plausible, sort of based on the data that we got. These are data supported estimates or not. Sort of talking about uncertainty, right? I'm not saying here, can we say that the null hypothesis is true based on the second example? No, it doesn't tell us the null hypothesis is true. We're just saying our data are pretty inconclusive. Like, I don't know, our data would support anywhere from a 4-point decrease to a 12-point increase. So who knows, right? And so we could say, yeah, there's not a significant difference. That's not sort of as rich a meaning in terms of just sort of recognizing that, no, the data that we got are fairly compatible with the null hypothesis. So sort of our point estimate is 84, but population value is well within those bounds. So we have anywhere from a sort of a slight decrease to a large increase. So, but what's the big caveat to sort of all of these scenarios? What's the big thing that's lending to our imprecision in these data? Yeah. Yeah, the sample size, right? exactly. What's that going to do, Kate, to my confidence bound? Yeah. This number is going to go way down, right? And as that goes way down, what happens to my interval estimate? It shrinks way up, right? And so we'll get into this when we talk about the philosophy of null hypothesis testing. So if I know that if I just collect 1,000 people, that everything's going to be different than 0, what's the use of the exercise, right? And so, yeah, we might find sort of based on this, it could be because there's actually not a difference, that sort of the population, sort of in older adults taking supplements, the values are actually pretty close to 80 and there's no difference. Or maybe we're not finding a difference just because we've got a small sample size. We don't have the power to detect the difference that's there, right? And so all of this stuff starts to go through, and it's kind of like pulling back the veil from our methods and to recognizing that we can really easily start to fool around with this stuff. But if you know kind of what those things are, helps to develop better inferences about what's happening in your data. Yeah. Mm-hmm. Mm-hmm. Yeah. It helps if we're using metrics that have some sort of intrinsic meaning, right? Like the height, right? When we saw the standard error of height is a little over a ½ inch. I know what height is in terms of this, right? Here, I mean, I would hope that the standard error of my estimate would not be anything even remotely close to my standard deviation. Here it's sort of a fifth of the size, but that's still pretty big. And then, Haley, if we go through look at what happens when you plug that into that confidence bound. I mean, I don't know what 80 means in terms of the scale, but I don't know anything from this to this, right? And sort of the thing was we talked about what a value of 7 points or something like that, talking about that as impactful, right? So, and I did that to just help you trying to sort of make some reasonable interpretations in this hypothetical scenario, kind of where that goes. If sort of just based on the sample size, you should assume that your standard error is going to be pretty large with that stuff. Yeah. Here in our supplement scenario 1, where we've got a mean of 92, we've identified our alpha level as 0.05. Critical values then on my curve are plus or minus 1.96. My mean of 92, confidence bound, and then my z-score of 3 is hanging out here. I'm way outside the bounds of sort of where my benchmarks are. And so in this scenario, I'm going to go through, and my conclusion is going to be to reject the null hypotheses. And so my conclusion is going to be that if older adults who are taking supplements, if the mean cognitive score is actually 80 in that population, it would be very unlikely for me to obtain a randomly selected sample, 25 individuals who had an average cognitive score of 92 in this situation. Okay, this p-value, that graph pad at the bottom, you go through and pull that off of the table because it's a nice round number, but that's where I look. If you go down to that graph pad, then there's a lot of different ones you can go through and find. You just punch in your z-score for a two-tailed test. It'll give you that p-value there. Scenario 2, where I've got a mean of 84. Again, same alpha level, same critical value, but this time estimate is much lower. My confidence bound runs from 76.2 to 91.8. And if I go through and document where my z-score of 1 is, it's well within that body of the distribution, right? It's not what I would expect. It's not 80, but it's still relatively compatible with what I would expect if the null hypotheses were true, right? So if older adults who take supplements, if the mean cognitive functioning score in that population is 80, it's not terribly unlikely for me to get a score of 84. So I would just say data are inconclusive. I'm not saying that the population value. Yes. If you say, could it be 80? I'm like, sure, my data certainly support that possibility. So, and this is the thing, when we get into sort of null results, we can never say that we've sort of ruled out the null or proven the null wrong or accepted the null or said the null hypothesis is true. It's just inconclusive. Right? All we can do is say, I don't know. Right. All right. Here's where we get Jalen on one-tailed versus two-tailed. In the two-tailed test, what we do, and we're just going to run through this quickly. We're not going to do a whole lot with one-tailed test, but in our two-tailed test, what we're doing is we're splitting our critical region in half, right? So it's 0.05. So I'm going to find the marker where 2.5% is in the upper tail, 2.5 in the lower tail. And sort of my probability value for the two-tailed test is going to be multiplied by 2 to account for the possibility of things hitting sort of above and below, right? And so most of the stuff that we do, we say like, I don't know, but if it falls in either tail, we're going to claim evidence against the null hypothesis, okay? One-tailed test is where we're starting to get a pros and cons situation. And in directional test, what I'm doing is I'm putting all of my critical region into the upper lower tail. I'm saying it's either sort of going above or below, okay? And here the p-value for my test statistic is reported without consideration of sort of what might happen in other tails here, okay? Basically what we're saying in my directional tests are nice and they've had a history in terms of like, hey, I'm calling my shot. Like if it's lower, I'm not going to claim credit. If it's below, I'm just saying it's all sort of in the upper end, right? And so from a traditional experimental approach, right, some value to claiming one-tailed tests or specifying one-tailed tests. And if I'm doing that, what happens instead of having 2.5 and 2.5, I put all of my 0.5 into one tail. And so what does that do to my benchmark on that side? Makes it more reasonable. It's 1.68, right? Now, the downside is that a lot of times things that we might do that we think are going to help sometimes don't. Sometimes they are in the opposite direction and are very much not helping anybody. In a one-tailed test, I ignore that because if it's anything below, I don't care about it. I'm not going to count it. A lot of times there's stuff, if it's going way in the opposite direction, that's relevant information to know. But in a one-tailed test, I ignored it. Could be, I could get a z-score of -5, but I'm not going to say anything about that because I'm putting all my eggs in that upper division basket, okay? When we get into calculating confidence intervals, it starts to get a little bit more complicated here. Technically, what we're doing is calculating 90% confidence intervals for alpha equal 0.05 test and just looking at the bounds on sort of the upper end, ignoring everything on the lower end. You don't see this a whole lot. If you run into or have occasion to create confidence bounds for a one-tailed test, come talk to me. I'll help you work through it. We're not going to work on it here. I don't want to spend a lot of time working on it. Essentially, in this first supplement, we would say if we're doing a one-tailed test, my critical value is now 1.65 because I put everything in the upper tail, right? Here's my z value of 3, right? But technically, my confidence bound runs from 85.4, the lower bound, to infinity, like sort of whatever. Like there is no upper bound. I've got a lower bound that's sort of farther back than it was with the two-tailed test because I'm sort of putting everything here. And so this benchmark is smaller than the 1.95, right? So it's going to expand things out. But I just don't have an upper bound because I don't care about the upper bound. It's just the lower bound that I care about here, okay? Same thing with this scenario. Here, my value of 1 is to my critical value than it was before. Confidence bound is going to be anything from 70, right? Just kind of how you don't see these a whole lot. So don't worry about it too much. We're not going to do too much with directional tests here. Pros and cons with these. You sometimes will get in trouble. I mean, but sometimes there are scenarios, and a lot of times there are scenarios where, like, no, my guess is that this is going to improve, and if it doesn't, if it's down, like I don't care about that, and I'm just saying this. But then we can go through what'll often happen is reviewers will get skeptical that you actually called that shot on the front end, and because it's moving back the goalpost, it makes it easier to cross that threshold. And so even if you do have very clear directional hypotheses, people will still generally want to see two-tailed tests just because it's convention. Arguments for and against it. But for this class, we won't have to worry about it too much. We just have bigger fish to fry. So sound good? Awesome. Yeah, indeed. You always want to call that shot because once these rules all apply, if we're predicting beforehand, once we have information, that changes the whole philosophy of everything, right? And so this is what will happen sometimes is like people will go through, and Johnny, you had asked about like the use of alpha correction and corrected tests and things like that. Like oftentimes what will happen is people go through, take a look at their statistics and find that all the things that they're actually really interested in are p less than 0.001, and then have a come to Jesus moment where they decide to go through and create sort of like, oh, what I'm going to do, I'm going to bond for only correct everything, knowing full well that if you do it, it's not going to change anything and it's just going to make it look like I was super rigorous. That's no good, right? If you're going to do that, you need to do it on the front end. But this is why the one-tailed test starts to get, people will and understandably start to get suspicious, particularly if you have an effect that or a test statistic that would not meet criteria for interpretation in a two-tailed test. Now you're just claiming that it's a one-tailed test. I'm like, like, when did you make that decision, right? Now, from a traditional standpoint, experimental, there's sort of strong reasons for doing that. It reduces type 2 error, which is an error that we should be more concerned about. But it can kind of be a tough row to hoe sometimes with investigating. You have to be very, make a strong argument for laying out your stuff. And with pre-registration things and sort of the direction that that's going, that can be something that you may be able to do. Like, well, whether or not people buy into it or not, I don't know. But I think sort of we might see more one-tailed tests with some pre-registration stuff. It's just hard for me as a reviewer to know what was in Jalen's head sort of before she collected the data and sort of when all this stuff kind of emerged, right? So that's some of the sort of the stuff that goes into that. All right. Last thing, we want to draw a conclusion, right? We wanted to sort of pull in information about range of population values, precision of point estimates, effect sizes. We'll get to these later based on our confidence bounds, right? Our options are we can hypothesis, right? This is what we're doing. Test fall. To highlight this line here, we're assuming it suggests that the sample data are unlikely, assuming that null hypotheses and all corresponding assumptions of the statistical model are true. So assuming that the null hypothesis is true, and we haven't violated any of those auxiliary assumptions that I do have random samples and good measures and representative samples and things along those lines, then if I reject the null hypothesis, then I'm assuming that these data are unlikely if this is actually the case. And because of that, what we do is we assume that the sample was likely drawn from a population with a mean that was different than the one that was specified under the null hypothesis. We're saying that if the null hypothesis is true and I've done everything correctly, these data are extremely unlikely. And because these data are extremely unlikely, it's sort of there's a good chance that these data were actually pulled from a population that has some mean value that's not the same as what I specified under the null hypothesis. Okay, and we take this as indirect support for the alternative. We never claim support for the alternative. We just sort of fail to reject the null. Right? Are these data compatible or incompatible with the null hypotheses? If they're incompatible with the null hypotheses, it's kind of implicit support for the alternative, but we never say that we find support for the alternative or that we prove the alternative or any other thing. Okay, and we'll talk about why that is. Fail to reject. This is when we have a test statistic that falls within the body of the distribution and sort of basically says that that the sample data are plausible, assuming that the null is true. Right? We're not saying that the null is true. Right? Again, we sort of all we can do is that we say that we have insufficient evidence to claim an effect. right? And this is a sort of this atheist versus agnostic thing. I'm not saying that the null hypothesis isn't true. I'm not saying that I've proven that the null hypothesis isn't true. All I'm saying is I don't know. The null hypothesis could be true. It might not be true. I'm not taking a position either way. All I can say is that my data seem to be compatible. If this were a true thing, these data would seem to fall within what we would expect sort of based on this. So I don't know. Different sample, bigger sample size, different things might turn out. I'm just saying that the data are inconclusive. I can't really say one thing or another. Okay. All right. And again, fail to reject does not prove that there's no effect. Okay. Fail to reject, it doesn't say that there's no effect or that these populations don't differ. All I'm saying is just that my data don't allow me to claim support for that effect. Okay. Wilkinson. Never use the unfortunate phrase except the null hypothesis. Okay. Someone will. It'll happen. So Matt will get super aggressive. I'll have to go in and ask him to calm down, right? But it'll happen. Try and avoid it. Terrence. We were actually sitting by a pool and I was reading a statistical paper. Conclusions here. So this is just me kind of writing out kind of what how I might go through and write up some of these results here. We say point estimate of mean cognitive functioning, 92 data in the study suggesting scores from 2 to 99.8, reasonable lower and upper bound, probability of randomly selecting a sample. Don't worry about this piece, ignore this piece of this. So that's just a literal interpretation of the p-value. Don't worry about that too much. But test values fall within the critical region set by alpha 0.5, assuming no meaningful violations of assumptions. Conventional decision rules recommend a rejection of the null hypothesis. But here, this is where we're kind of getting in the meat and potatoes, right? So it's saying it's important, however, that estimates supported by these data are compatible with meaningful elevations in functioning relative to general population of older adults, as well as lower bound estimates falling below the threshold of practical effects, right? So whereas the data offers support for higher assessment scores in older adults reporting regular antioxidant use, additional data is needed, which these are consistent with meaningful effects and probably something that sort of involves more controlled tests and larger effects. So we got a signal. We're saying like, hey, things are looking promising, but sort of with sort of where we're at, we can't really say kind of where this is at, and sort of our data supported values for the actual effect range from anywhere from super massive to something that's pretty trivial. So want to take that into consideration. Okay. Same thing with this, using just kind of different and sort of go through. This is not a template. Do not template any, like, this is my stuff. This is stuff that I wrote. This is mine. You can't have it, right? This is something for you to go through and kind of take a look to kind of get a sense for what I am thinking about is kind of a nice sort of way to go through and sort of integrate the information that we're getting from this. But again, just use your own words, right? Take a look at this and try and get a sample, but then don't look at this while you're writing your own interpretations, kind of bullet out like sort of what are the things I want to touch on, and then how do I go through and say that. Here we're saying, although data are compatible with the estimates suggesting meaningful elevations in functioning relative to the general population of older adults, the study is at best inconclusive with respect to statistical practical effects. We just can't say much of anything here. Okay, so just go through, take a look at those as example, but please do not try and copy this, because what'll happen is I'll read it and I'm like, God, that's brilliant. I'm like, wait a minute, that's because I wrote it and I sort of really like that. So, all right. We'll stop there. We'll pick up with error stuff. Any questions before we let you break? All right, cool. We'll keep you posted on whether or not I make progress on getting those assignments scored back to you tomorrow. If not, we'll just push back the due date on that. So you can go through and adjust your schedules accordingly. All right. Awesome. Thanks, folks.